Welcome to this webinar. The subject is hydrogen domestic gas metering. My name is Mark MacDonald and I'm Head of Clean Fuels at Tuvsud National Engineering Laboratory. I'll refer to the company as NEL now just to save time. My background is I studied chemical engineering at Strathclyde University in Glasgow, and I've been working with NEL for the last 9 years. I spent quite a bit of time in our laboratory facilities doing testing, calibration, and research on various different technologies, mostly flow meters for oil, gas, and well, a lot of time I've spent on multi-phase meters as well. In 2018, I started to lead our newly formed Clean Fuels Group with a focus on flow measurement for hydrogen and carbon dioxide. A lot of that time has been spent designing calibration facilities and new primary flow standards for those applications. So that's really the subject of this presentation, with one of our facility designs for hydrogen. So let's get started then. So there's a couple of different sections in this webinar. First of all, just a general introduction to why measurement is important in industry, and some background on the net zero challenge and the role that hydrogen can have in removing carbon dioxide emissions. Then we'll look at some of the challenges with hydrogen metering specifically. And finally, at the end of the presentation, we'll look at the design of our facility and some of the work that we intend to use it for. So to start off very simply, why should people care about measurement and why is it important to industry? So the way we look at it is that measurement has an enabling role for many industrial processes and to facilitate trade as well. So a really simple example is to imagine that you wanted to buy large quantities of a raw material, or if you wanted to sell your own goods. And for that to happen, both parties have to have confidence that the transaction is carried out in a way that is fair, accurate, and legal, and exchanging the correct quantities, whether that be mass or volume. That's a really crucial part to that transaction. Other examples are for safety purposes and for engineering practices. We need to know that the measurements our calculations are based on are accurate. So there's lots of ways that it's maybe not so obvious to the average person, but if you're working in measurement, it becomes a bit clearer, the supporting role it has for many industrial processes and in the wider economy. So a good example of this is when you refill your car with petrol or diesel, or maybe hydrogen in the future. Most of us don't really think, how accurate is that dispenser? Although if you work in measurement, you're more likely to think along those lines. And I think that's really a sign that the measurements are accurate enough for the application, because people don't concern themselves with it as much. So that's really the state that you want to get to most of the time. You want to make sure that measurements are accurate enough that people don't really consider them. And at that point, it's almost as if the measurement process becomes invisible because it's working correctly. On the other hand, if you have large errors or discrepancies, that's when you get disputes between two parties, or you get situations where consumers feel like they've been, well, basically, they've been shortchanged, you could say. So that's really the scenario we want to avoid. So within the UK, we have the National Measurement System, which aims to make sure that measurements taking place in the UK are accurate, fair, and legal. So this is something that's funded by the Department for Business, Energy and Industrial Strategy, with around £65 million per year invested into this system. The overall aim of which is to promote good measurement practices, to develop the UK's measurement traceability chain, developing documentary standards so that people are more aware of correct measurement practices, and to enable further dissemination of good measurement practices through knowledge transfer and presentations like this one, for example. And also, there are sometimes measurement challenges that aren't being addressed without this level of intervention. So the Department for Business, Energy and Industrial Strategy, BEIS, will often fund metrology research projects in order to solve some of these larger challenges. So hydrogen flow metering is a good example. Most people have some awareness that this is something that has to be resolved. There's many challenges involved, but we don't really know the best way to a solution at this point, and it's going to take a significant amount of research. So within the national measurement system, you have different laboratories that are carrying out the research and the technical work. So for example, you have the National Physical Laboratory, NPL, which develops and maintains standards for the fundamental SI units, such as distance, time, temperature. You also have the National Institute for Biological Standards and Control. They develop standards for biological measurements. You also have the Laboratory of the Government Chemists at the NML, so they develop chemical standards. Our role at NEL is to develop standards for flow measurement and density. And you also have the gear design unit at Newcastle University, who are obviously working with gear metrology. And also the Office for Product Safety and Standards, who are more involved with the regulatory aspects, but they also have measurement capabilities as well. So I mentioned the traceability chain on the previous slide. So I just want to go into more detail about what that actually means. So the way to think of it is, if you have traceable measurements, that means that you have a calibration history and you have reference points towards standards, whether they be national or international. So the diagram is set up in a way so that you look at the top of the pyramid first and how decisions made at the top filter down to the end user. But in some ways, it's easier to describe it if we start from the bottom. So if we are a person in the wider economy who's using a measurement device that they just bought, so what kind of expectations can they have for its performance? So if, for example, it's a flow meter and you're not too concerned about the accuracy, maybe you're happy to accept errors of 2 to 5%, for example. Even in that scenario, you still want to have some reassurance that this device is consistent with other ones that you've bought from the same model. So you want to have consistent performance regardless of how many of them that you buy. So to have some assurance of that, the company that you buy them from, the manufacturer, they will typically have a quality control and quality assurance department, and they will be very interested in that sort of criteria. So how consistent are these devices within a batch? And they might be looking for performance of maybe 1% errors at that stage. And the way that they'll ensure that is that they take representative samples of the production and they'll send them away for calibration at accredited laboratories. So those accredited laboratories might have flow measurement uncertainty of less than 1%, maybe they'll be down at 0.5% or so. And they take their traceability from national measurement system laboratories. So in each step of the process, we're working back towards national standards, which themselves will have an even lower measurement uncertainty, typically around less than 0.1% for flow measurement applications. So that's where we sit within this table. NEL are one of the organizations listed as a national measurement system laboratory. At the very top of the chain, we have BASE, who are setting the strategic and regulatory framework, along with the Office for Product Safety Standards. And as well as making the decisions on how measurement practices should be carried out, they also invest a significant amount of money into research for new measurement areas and also for the ongoing maintenance of standards which have been developed. So that covers the traceability chain and how this affects the end user. So moving on to the net zero challenge, part of the background, part of this presentation. I'm sure most of you are aware that governments and companies around the world are now thinking increasingly about reductions in carbon dioxide emissions and the use of clean energy technologies. It's worth just looking at what some of the drivers for this are. So there's various policy and regulatory drivers throughout the world and Europe. You've got the Paris Agreement, which aims to limit the global temperature rise to less than 1.5 degrees. There's the Renewable Energy Directive, which is an EU directive for encouraging the use of renewable technologies. There's also the European Green Deal, which is a whole raft of policies, which again is aiming to achieve climate neutrality by 2050. And within the UK, we have the Climate Change Act of 2008, which has the overall aim of making sure that the UK is carbon neutral by 2050. So these are quite ambitious aims, and some serious thought and some serious work is required to make this happen. So There have been various documents being written on the subject, but an interesting one from the UK is the Clean Growth Strategy, which was written in 2018. And in it, it first of all identifies where most of our carbon dioxide emissions come from. So in the UK, around 56% come from the transport and heating sectors alone. So these are targeted as key areas to decarbonise in order to remove these carbon dioxide emissions. And in this document, it's quite agnostic about the approach that could be taken or the technologies that could be used. So the Clean Growth Strategy for the UK recognises the role of electrification through the use of solar and wind technologies and battery electric storage, and even heat pumps for domestic and commercial properties. It also recognises the role of biomass and bioenergy. So anaerobic digestion has been increasingly, anaerobic digestion plants have been increasingly common in the UK in recent years, but it also recognises the role of hydrogen for decarbonisation of various different sectors. And finally, there's various mentions of carbon capture and storage as an enabling technology for hydrogen generation. So specifically looking at the hydrogen part, as I said, there's many different areas where it could come into play. So first of all, on vehicle transport, hydrogen is seen as being quite a decent option for heavy duty transport. So it potentially can offer, fuel cell vehicles powered by hydrogen can potentially offer greater range and shorter recharging times than those powered by battery electric vehicles. Of course, there is a cost in terms of energy efficiency, but one of the main advantages to hydrogen is that it could also be used as a method of energy storage. So with renewable electricity, we don't have control over the sun, we don't have control over the wind or even the tides. So one of the issues with renewable energy is that it's intermittent, and sometimes you generate too much energy that you can't even use. If you have a means of energy storage, then that potentially means you can access energy that would otherwise go to waste. So hydrogen is seen as being potentially a very useful way of storing that energy. So during periods of peak solar or wind generation, you could generate hydrogen from electrolysis, which means even though the process might be slightly energy inefficient, it does mean that you have access to this energy that would otherwise go to waste. There's also the use for hydrogen for heating applications. So this has been investigated in quite a big way in the UK and other countries for the potential for decarbonisation of the gas networks. So even within domestic properties, there are studies looking at the possibility to use hydrogen instead of natural gas. So there are some advantages to this in that you'll be able to use the gas network infrastructure and the skills and knowledge developed in the gas industry in the UK for a different purpose, rather than going with a full conversion to electrical appliances. But also within industry, there are some applications where you have to apply heat through direct flame applications, and there isn't really a suitable electrical alternative for those. So to decarbonise, burning hydrogen might be the best way to do it. And as well as energy storage, hydrogen potentially offers a means of energy transport as well. So it can be transported in various forms as a compressed gas in cylinders or through pipework, or even as a liquid form, or as part of as a metal hydride, for example. So that there's various options there. But the point is, in that previous document I mentioned, the Clean Growth Strategy, all of these different pathways are mentioned as potential uses for hydrogen to enable decarbonisation in the UK. But you see similar plans in other countries as well. So there's a few areas that we are very interested in. NEL as the National Measurement Institute for Flow and Density. The areas that we're working on right now are hydrogen flow measurement for vehicles and for the gas grid, but also flow measurement of carbon dioxide for CCS applications. But I'm going to focus on the second point on that bullet point list, hydrogen and the gas grids. That's the focus of this webinar today. So for some more background, there is, like I said, a lot of projects investigating the potential to use hydrogen within the gas networks to displace natural gas and to achieve the removal of carbon dioxide emissions. So there's various projects that you've probably heard of, including H21, HyDeploy, H100, and Hy4Heat. NEL isn't a partner in any of these projects. I'm just mentioning them here to give some background. But those projects focus on various aspects, including safety, technical feasibility, and quite a lot of social science and looking at the public attitudes towards the use of hydrogen. But within those projects, most of them have some recognition that flow metering has to play a role as well, because this is how people receive their energy bills. Everybody has a gas flow meter installed on their house. So if there are performance differences when you use hydrogen instead of natural gas, then that directly impacts on the billing accuracy. So the first project that's worth mentioning is H21, which is led by Northern Gas Networks. The project partners include Cadent, SGN, Wales and West Utilities, National Grid, DNVGL, and the Health and Safety Executive. This project's actually been running for a while now, so they first published a report in 2016, which was the Leeds Citygate feasibility study. And the conclusion from that report was that it would be possible and economically feasible to decarbonise the gas distribution networks in the UK through conversion to 100% hydrogen. This was followed up by the H21 North of England report in 2018, which provided a more detailed engineering solution for how this could be achieved for 3.7 million homes in the UK between 2028 and 2024. And the plan would then be to increase this to a further 12 million homes by 2050. So as you can imagine, this is quite a big project with various different aspects to it. There's a lot of study on safety aspects, the effect of hydrogen on different pipeline materials, the consequences or the likelihood of hydrogen leaks and the consequences when that happens. So does it pose more of a risk compared to natural gas? And if it does, how much more of a risk does it pose? But there's various different parts to this project, and we're quite happy to see that metering has been considered as well. So early on, the project partners realised that metering could be affected by the change in gas, and that accuracy forms part of the public acceptance angle. So that's an encouraging sign for us as a measurement institute. So the photo on the right-hand side at the bottom, it shows some of the polymer pipes which are used in the UK gas networks. And these have been increasingly common on the low pressure side of the gas networks, so the local distribution and domestic metering side in recent years. So the gas networks in the UK have been upgraded over the last 10 or 20 years or so. And this is the type of material they've been using for the piping instead of the old iron and steel pipes. And that wasn't done with any inclination towards hydrogen, but it turns out that this material does seem very suitable for use with hydrogen, even up to 100%. So that's part of the focus of this project. H21 is looking at local generation and distribution of hydrogen through the low pressure networks in the UK. So they're not so much focused on the national transmission line, because that would be a much more significant upgrade, and it operates at higher pressures, so there's more risks involved. But at the low pressure side, pure hydrogen is seen to be a feasible option, which is really interesting. A slightly different approach is taken by the HyDeploy project. So HyDeploy is focused on 20% hydrogen blends with natural gas. The project is led by Cadent, one of the gas network operators. And the project partners also include Northern Gas Networks, Keele University, the Health and Safety Executive, ITM Power, and Progressive Energy. So the reason this project is focusing on 20% hydrogen is it's thought that that's the maximum that the standard pipeline materials and appliances that we have already could tolerate before they have to be replaced or upgraded. So the project is very much focused on collecting the evidence for that. And the first phase was a demonstration at the Keele University campus, which has recently been completed. So they had the campus gas grid, which is isolated from the main UK gas grids. We had that operating with blends of up to 20% hydrogen. And the idea was that none of the appliances on the site would be replaced, and things would continue to operate as normal, and they would just collect the evidence to show that this is safe and technically feasible. So, as I said, those tests have been completed recently, and if you visited Keele University during that time, you wouldn't really notice any difference. Like, you wouldn't know that the gas circulating throughout the system was 20% hydrogen, and people just went about their day as normal, and there wasn't any major differences to the pipeline installations, other than a separate compound which introduced the hydrogen to the site. So that was a really interesting development, and it's good to see practical demonstrations of that type of scale. But in the second and third phases of the project, the partners are going to move towards larger networks in the northeast and the northwest of England. Another project that is focusing on pure hydrogen is H100, led by SGN, and they have project partners including Kiwa, Gastech, Providence Policy, DNVGL, HSL, ERM, National Physical Laboratory that we mentioned before, University of Edinburgh, Steer Energy, Costain, Arup, and Wood Group. So there are some similarities with this project in H21, although this project is focused not so much in the north of England, but actually in Scotland. And they have a demonstration project in Fife, which is going to be starting quite soon. But there are some similar areas that are investigated. So safety implications of using hydrogen, the compatibility with different pipeline materials, logistics, there's some social science and investigation of public attitudes towards this change. But again, there's some interest in hydrogen flow metering, which is encouraging. Like I said, we usually see that industry doesn't always consider the difficulty of flow measurement until they need that capability. So for us to develop calibration facilities and primary standards, we need to have as much notice as possible when this is happening. So it's good to see that flow metering has been considered at the early stages. So one of the big demonstrations in this project is a demonstration of 100% hydrogen at a site in Leavenmouth, Fife, where they aim to provide hydrogen to up to 300 homes in 2022. So the hydrogen may be generated from offshore wind energy, and we'd have some storage capacity to deal with the intermittent nature of that supply. The way this works is that people in that area have the option to operate with hydrogen. So they can have hydrogen provided to their homes. And if they do, then they are given new appliances which are considered hydrogen ready. And the cost of their gas consumption is price matched to what it would be with natural gas. Other people can choose to opt out and just operate their appliances with natural gas as normal. But again, it's quite a big demonstration project, and it's encouraging to see this type of work taking place in the UK and providing some of the leading research in this area. Finally, from the UK projects, there's also Hy4Heat, which is led by Arup on behalf of BEIS. And project partners for the project management side of things include Kiwa Gastech, Progressive Energy, Embers, and UO Energy. But there's actually a lot of manufacturers involved in this project to provide new appliances and hydrogen technologies. So this is once again focused on 100% hydrogen, but the focus is very much on developing those new appliances, including things like gas boilers and cooking stoves and even flow meters. So you can see some of the areas that are studied here. There's the development of various different technologies, including 2 manufacturers of flow meters for hydrogen domestic gas metering. But there's also some study on the need for the requirements for gas purity of the hydrogen to ensure a clean burn, and also a study on what odorants and colorants and odorants should be added to the hydrogen. And because when hydrogen burns, pure hydrogen doesn't have a visible flame, so additives are needed to make the process more safe. And similar to natural gas, you need odorants as well to make it more obvious when there's a leak. So those are the UK focused projects. As I said, NEL aren't actually working on any of those. It's just to give some background to this area. There's also some European projects. So I've only mentioned 2 here, which are the GRHYD project in France and the Power to Gas project in the Netherlands. But there's various different examples, and there's lots of variations on similar themes. So some are looking at pure hydrogen, some are looking at 20% hydrogen, and there's usually some form of demonstration project, either using an isolated part of the gas networks or demonstrations with actual domestic properties. So there's a lot of work happening in this area, not just in the UK, but in Europe as well. So focusing on decarbonisation of the gas grids, this is really going to be a crucial part of achieving net zero emissions by 2050, because as we showed before, it's a significant contributor to our carbon dioxide emissions. So the use of alternative gases such as hydrogen is a really important area of study, and we can see there's lots of demonstration projects which are looking at this issue right now. So as I said, most of the focus is on safety, material compatibility, technical feasibility, but we do need to think about the accuracy of flow meters as well, because this affects the billing accuracy, which factors into the customer perception. So there are 2 different considerations. Are we using pure hydrogen, or are we using a blend with natural gas? Because the performance could be different for each. There is actually a project investigating this area, which is the new GasNet project, the full name of which is Flow Metering of Renewable Gases. So this is a project funded by MPR, which is a European project, sorry, the European Programme for Innovation and Research. And that ultimately is funded by Euromet, which is the European Association for Metrology Institutes. So this is a 3-year project which started in 2019. And the overall aim is to study the flow metering aspects when they're operated with renewable gases, including biogas, biomethane, hydrogen, syngas, and mixtures of these with natural gas. So it's an entire project which is focused on flow measurement. And there's various project partners from metrology institutes, meter manufacturers, and gas network operators from across Europe. So you can see all the project partners on the right-hand side. TÜV National Engineering Laboratory is a partner working on the hydrogen flow measurements. If you're interested in this project, then I encourage you to go to the web link, because some of the first reports are starting to appear on the project website, and we're starting to do some of the more interesting technical work at this point in time as well. So it's worth following. If you look at the news section, you'll get the first glance at reports and data provided from the project. So some of the areas that are being investigated are, well, first of all, the revision to the CEN TC237 standards for domestic gas meters and OIMO R137, both of which are used as the basis for legal metrology in Europe for domestic gas metering. So we're currently working on the revision of those standards in collaboration with the flow meter manufacturers and the conveners of the working groups of that standardization committee. We're also doing some tests with various flow meter types, looking at the measurement accuracy, but also durability effects when they're operated with these various gases, including hydrogen. So the example you can see, the top photo on the right-hand side is a sewage treatment plant in Italy. And this is one of the sites where meters are going to be installed and operated with biogas for extended periods of time, several months. And an identical set of meters will also be tested with natural gas at the same time to compare what sort of aging effects do you see with the biogas compared to the clean natural gas. So the facility at the bottom left-hand side is a natural gas loop for testing various of these meters with exposure to with natural gas, which can be compared against the biogas tests. Similar tests are going to be done with hydrogen as well. The skids shown in the bottom right-hand side is a test bench for hydrogen flow metering accuracy. So those are various sonic nozzles, which have been, this skid has been assembled by the project partner PTB, and it's quite similar to the type of facility that NEL is using as well. But later on in the project, we're going to do more testing with the flow meters to determine their accuracy with these various gases, but also a flow facility into comparison. So this means that the test facilities used in this project will be compared against each other to determine what is the agreement between them, and are the claimed measurement uncertainties verified. So it's a really interesting project, and like I said, you should visit the website if you're interested in this area, because there will be a lot of data provided from the project. So now that we've given some of the background, I just want to briefly go over what some of the challenges might be with hydrogen flow metering. So we've seen that there's various projects considering the use of hydrogen, but why would the flow measurement side be difficult? Well, first of all, you have to think about the difference in fluid properties of hydrogen compared to natural gas. So one of the most obvious changes is that the calorific value of hydrogen is less than a third of that of natural gas. So this means that if you want to achieve the same energy density, you have to increase the flow rates if you're using pure 100% hydrogen instead of natural gas. And as you can imagine, it might mean that flow meters size for natural gas are now overranged. And if these are mechanical devices, not only will they have measurement errors, but they could see increased wear or premature mechanical failure. So there's an example given on the right-hand side from the standard for ultrasonic domestic gas meters, and it just shows you the standard flow rate ranges when operating with natural gas. As you'd imagine, this standard would have to be updated if the same meters are going to be operated with pure hydrogen. Other fluid properties are also significantly different. So density is one of the biggest one. So the density of hydrogen is 8 times lower than it is for natural gas. The speed of sound is 3 times higher, and the viscosity is lower, although it's not too different compared to the other fluid property differences. But again, you can see a scan from the standard for ultrasonic domestic gas meters, and you can see that the fluid property ranges of interest are things like speed of sound, attenuation, viscosity, and density, all of which are going to be different for hydrogen. So for this reason, we could expect that most of the metering technologies used for domestic gas metering could see a shift in performance at the very least if they're operated with hydrogen compared to natural gas. So what types of meters are used? Well, for domestic gas metering, there's 3 different types which are commonly used. By far the most common is the diaphragm meter, which is a positive displacement type. So with these meters, what we might see is that because hydrogen has a greater tendency towards leakage, that might mean that certain amounts of hydrogen can bypass the internal clearances within the meter and result in higher errors. But also these meters are less suitable to be used for higher flow rates because you would have to increase the size of the meter itself. Because as a mechanical device, they could be damaged by operating at too high flow rates. There's also ultrasonic and thermal mass meters. So these are more modern meter types, but as I said, they could be affected by the change in fluid properties. So for ultrasonic meters, we might be concerned about acoustic attenuation and the timing resolution of the ultrasound signal because the speed of sound is much higher for hydrogen. With thermal mass meters, we do need to think about changes in the heat capacity of the gas, depending on what kind of blend it is of hydrogen, and also if the heating element and the sensors themselves are appropriately specified. Of course, this is just speculation, and the real value will come from doing the actual calibrations and providing test data to show how these meters actually behave. So there is an interest now in preparing evidence for this. So we would need calibration data for hydrogen. So this is a problem because until recently, there was no facilities available, and recently some have been developed or are being built at the moment, but there's still a lack of options here for performing the necessary research. And part of the problem is, what would you use as a reference flow device? Because if there isn't previous performance data for flow meters operated with hydrogen, it doesn't really give you many options for a reference flow meter. So this is something that we had to think about. Back in 2018, we had our first inquiries into this area. So NEL were approached by a gas network operator to support some of the UK demonstration projects, and there was a requirement for calibrating domestic gas meters with pure hydrogen. And what this meant was that meters normally operated at 6 meters cube per hour would have to be operated at higher flow rates, so closer to around 20 meters cube per hour. And they would have to be assessed against the EU Measuring Instruments Directive, maximum permissible errors of 1% or 1.5%. So this gave us some indication of what kind of capability we needed. So we needed a reference flow device which was suitable for very low gas flow rates, much smaller than what NEL usually operates with. So our facilities are typically a much larger scale than this. But we also had to achieve very low measurement uncertainties. So if there's a maximum permissible error of, say, 1.5% for the test meter, then you really want a measurement uncertainty of multiple times less than that. So we aimed for 0.3% measurement uncertainty for hydrogen. But that's fine, that defines the need, but we still had to think quite carefully about what reference device to use because, as I said before, there was no obvious options to use as a reference flow meter at that point. So what we decided to use as the reference device was critical flow nozzles, or sonic nozzles as they're otherwise known. So these are a type of secondary flow standard which are widely used by metrology institutes, and they're also used in industry as well, but they're not quite as common as other meter types. So these have a very simple construction. There's a single element with no moving parts, and gas is accelerated to the speed of sound at the throat of these devices. If we measure the temperature and pressure upstream, then we can calculate the mass flow rate from the known thermodynamic properties of the gas. So these devices are very accurate. They can achieve uncertainties of 0.2% or better with air, and they're also available in a wide range of sizes. So the ones shown on the right-hand side are from our larger gas facilities. They're not for the facility I'm talking about in this presentation, but we have a range of sizes there from throat diameters of 1.25 millimeters up to 16. So the bottom left is the biggest nozzle and the bottom right is the smallest one. And with the smallest nozzle, you can't even see the orifice because the size is so small in this photo. So we know that critical flow nozzles are very accurate and reliable, but how do they perform with hydrogen? Well, there is some evidence for this, and we know for other gases that the performance is very consistent with air. So if you calibrate a critical flow nozzle with air, you can usually operate it with nitrogen, oxygen, helium, argon, methane, or natural gas. These are all gases which are covered in the standards ISO 9300 for critical flow nozzles. Hydrogen is not included in that standard, but there is some evidence for its performance from the literature. So on the bottom left-hand side, we can see a comparison between air, nitrogen, helium, and argon, and this is provided from research carried out by CC. So you can see that the curves for the discharge coefficient for the critical flow nozzle, they're consistent with each of those gases, and the middle image shows a graph with hydrogen data. So the empty squares are the hydrogen data, the black triangles are data for air, as are the plus signs, they are also air data with a different primary standard. And again, you can see that there isn't any significant difference between the performance with these gases. So there is some scatter in the data, but it's basically the uncertainty of the primary standard used for the calibration. You're not seeing a systematic difference between hydrogen and air. And those lines are the calibration uncertainty of around 0.2%. So there's very good agreement shown in that data. Once again, that data was provided in a paper by CC. Finally, on the right-hand side, we can see a comparison by NIST with air, nitrogen, argon, and helium forming almost a single line. And this is with very small nozzle diameters at low Reynolds numbers. So this is the worst case condition for agreement between these different gases in terms of discharge coefficient. You can see that carbon dioxide does not agree with those other gases. So the fluid properties of carbon dioxide are significantly different, that you don't get a consistent discharge coefficient if you're using small critical flow nozzles at low Reynolds numbers. If you're using larger Reynolds numbers, then that approach would work. But in this case, we can see a shift of several percent in the discharge coefficient. So this approach doesn't work for every gas, but there does appear to be consistent behavior for hydrogen and air, which is exactly what we needed for our calibration facility. So this is the approach that we took. We are using critical flow nozzles calibrated with air, but operated with hydrogen. And we estimate that the measurement uncertainty for nitrogen, which is also used in our test facility, is around 0.2%. And we estimate that the uncertainty for hydrogen is around 0.3%. Our facility operates, well, it was designed for flow rates of up to 38 meters cubed per hour at 1 bar. And the minimum flow rate we could achieve using the critical flow nozzles is 0.43 meters cubed per hour of hydrogen at 1 bar. So it means that we can't quite reach the bottom end of a domestic gas meter unless we use a different type of reference device. But you can see a summary of the performance on the right-hand side. So the blue dashed lines are the accuracy requirements from the MID class 1.5, and the red dotted lines are our expected measurement uncertainty for the facility operating with pure hydrogen, and it cuts off at 0.43 meters cubed per hour, which is the minimum flow rate for the sonic nozzles. Later on, we decided to revise the design of this facility. So instead of just using it for pure hydrogen, we wanted to be able to calibrate meters with hydrogen and methane blends. So to do this, we had to greatly increase the minimum flow rate ranges of the hydrogen flow measurement for our facility. And as I said before, we couldn't use critical flow nozzles because we were already using the smallest size available. So we had to use a different reference device for the very low hydrogen flow rates. So we decided to use laminar flow elements for the hydrogen flow rates below 0.5 meters cubed per hour. These have been calibrated with hydrogen, but we're not quite as sure of the performance compared to the sonic nozzles. So at the moment, we're assuming that the uncertainty could be up to 1% at this flow range. So for the very lowest flow rates, you can see on the envelope on the right-hand side, our measurement uncertainty band does increase. But we think this is acceptable because we're only really using those flow rates when we're operating with blends. So the overall uncertainty in the mixture is actually smaller than that. So this facility was built at the end of last year, and we commissioned it at the end of last year and the beginning of this year. So it's now operational, and I can talk a bit more about the design. So in this diagram, we can see a simplified P&ID. I did actually have animations on the slides, but they aren't working. So those colored lines, they represent different gases. So the yellow is hydrogen, the blue is methane, and the green is a mixture. So you can see there's two different distinct sections for this facility. There's the section outside which houses our which has our gas supplies. So we have compressed gas bottles for hydrogen and methane, and we have our on-site supply of nitrogen, which are located outside our laboratory facilities. The black dashed line shows the boundary of the building, so all of the measurement equipment is inside our laboratories. And I can quickly talk about the path that the gas takes as it moves through the system. So if you look at the yellow line, it starts from the compressed gas supply, so we have hydrogen bottles at 200 bar. It then passes through a pressure regulator, which reduces the pressure to around 15 bar, which is what we need for our reference measurements. Once we're inside the building, we have a series of control valves, which are used to set the inlet pressure and flow rate. And after the control valves, we pass the gas through one of our critical flow nozzles or one of the laminar flow elements, depending on what reference flow rate we want to operate at. Downstream, we have the test meters operating at 1 bar. And we have some control valves downstream of the test meters, which means we can adjust the test section pressure slightly. But after the gas has passed through the test meters, we vent it to atmosphere. So we're continuously using gas in this facility. It's not a recirc loop. The methane takes a similar path through the system as the hydrogen does. So once again, you have control valves to set the pressure and flow rate. And then we have reference critical flow nozzles for the methane side as well. And downstream, those gases are mixed, which gives us that green highlighted section. And the mixture is passed through a heat exchanger, which allows us to control the test section temperature. And it's passed through a static mixer before the test meter to make sure that the gases are properly distributed. Both the methane and the hydrogen sides could be operated with nitrogen as well. So we can use nitrogen as a test gas, but it's also used for purging. And there's various safety considerations here as well. So the parts of the facility which are inside our laboratory buildings are actually inside a separate enclosure as well. So this enclosure is continuously ventilated and it's equipped with gas detection. So if there is a leak detected or if the extraction system stops running, the system shuts down so that the operator is protected from these flammable gases. So you can see how the facility actually looks on this photo on the right-hand side. And I've annotated it just so you can see the different sections. So this is everything inside the hazardous area enclosure with the ventilation. The red section shows you the hydrogen reference section. The blue section is the methane reference section, and then the green section is where the mixture flows through the test meter. So we have hydrogen flow rates of up to 38 meters cubed per hour, and mixture flow rates of up to about 50 meters cubed per hour. We can operate the facility with pure hydrogen, pure methane, pure nitrogen, or a mixture of any two, with varying hydrogen concentrations. Our reference uncertainty is around 0.2% for nitrogen and about 0.3% for hydrogen. It's slightly higher for methane right now because we're seeing that there isn't consistent performance of the critical flow nozzles with the air calibration transferring to methane. So we do have to have we need to get our methane critical flow nozzles calibrated with methane to reduce that uncertainty. But the system is up and running at the moment. We can at least test, even if we need to improve the measurement uncertainty. The test section will usually operate at 1 bar, but potentially we can increase the pressure. It's just that most of the meters we want to test are domestic gas meters, which have a very low pressure rating already. So that covers the facility design. There's various activities that we're actually using it for. So first of all, at the moment, we're actually doing some testing to support the HyDeploy project that I mentioned previously. So we're testing a representative sample of domestic gas meters with blends of 20% hydrogen and methane. And we've got various different meters of different types. Most of them are brand new, but some were actually supplied by the HyDeploy project. So they've previously been operated with the hydrogen blend for extended periods at the Keele University site. So it means we can compare the performance of these meters that have previously been operated with the blend versus brand new meters. So if there's any sort of durability or aging effects because of the hydrogen, that would show up in these tests. Later on in the year, we'll also use this facility for the new GasMet project that I mentioned previously. So at the moment, NEL are working on the evaluation of the CEN TC237 standards for ultrasonic and thermal mass and domestic gas meters. We're working on that in collaboration with meter manufacturers and also the working groups from TC237. But towards the end of this year, we'll test some domestic gas meters with pure hydrogen for that project. And we'll also participate in a facility into comparison with the Metrology Institute's PTB in Germany, and VSL in the Netherlands, CMI in the Czech Republic, and also the meter manufacturer Metersit. So that inter-comparison will provide us with evidence for the actual measurement uncertainty of our facility. So we'll be able to see if we can achieve the claimed measurement uncertainty I've listed before. In the longer term, we do want to improve this system further by building our own primary flow standard, which would allow us to calibrate the reference critical flow nozzles and laminar flow elements with hydrogen and methane. So this is something we're starting the design of right now, and basically it would improve the traceability chain for our facility and reduce the measurement uncertainties as well. So we should be able to get closer to 0.2% for hydrogen and methane. So this facility would mainly be used for the calibration of critical flow nozzles, but also flow meters as well. And we'll design it so it's useful for hydrogen, but also methane, nitrogen, air, and carbon dioxide and other gases that we'd be interested in testing. So we're aiming for flow rates of up to 100 meters cubed per hour. So it is a small system, but the aim is still to have a hydrogen primary standard. And the target uncertainty for that facility would be 0.1%. That takes me to the end of the presentation. I hope you found this webinar interesting and informative. If you've got any questions at this point, I'd be happy to answer them.
Many thanks, Mark. Excellent presentation. Really, really good. I know you've done very well so far, but you're not quite off the hook. Just a few questions, if you don't mind. Thanks everybody for sending them in. There's a lot of interest here. No pressure, Mark, but here we go. I've got one here that, yeah, good question. Have you tested Coriolis meters with hydrogen?
Not yet. We're planning to test Coriolis meters used in hydrogen refueling stations in a separate project, not using this facility.
Right,
but
okay.
for this facility, we do want to test small Coriolis meters, so we're limited in size and flow rate ranges, but I know that you can get Coriolis meters in that size range, and I think we'd be interested in testing them, so I'd like to do that sometime this year.
Kind of answers the next question. I was going to say any plans for larger meters, but obviously you've just pretty much covered that. That is down the pipeline, as it were.
Well, we're still limited in size with this facility, so we potentially can upgrade it to slightly increase the flow rates and pressure ranges, but it doesn't really cover meters at the distribution scale in the gas networks. So for that sort of application, we would need to build a different facility, and it's something we're interested in doing, but we need to make sure that there's justification for it. So we do expect to get some evidence for this facility for the types of meters that are going to be used in larger applications, and I think that's going to inform the next step for us.
Okay. This is one I was going to ask, actually. Why didn't you build a recirc facility?
Yeah, I mentioned that we're using gas continuously, which does mean it's an extra cost for the tests. The reason for it is that we started, well, there's a couple of reasons, but the first reason is that when we started in 2018, we were only looking at a pure hydrogen system, and I did consider building a closed loop system, but at the time we couldn't source suitable fans for the flow rate ranges. So the flow rate ranges aren't challenging in any way, but there wasn't off-the-shelf options for a circulating fan. So we got quotes back which were very expensive for custom units. So that put us off straight away. But also, now that we're operating the facility with blends of methane and hydrogen, it's easier for us to get the lowest measurement uncertainties if we keep the methane and hydrogen separate until the test meter location. Because if you try and get accurate fluid properties for mixtures containing hydrogen, a lot of equations of state and fluid property software, they don't really give sensible results. So that's something we had to worry about with this test facility, because we had to have accurate densities of the mixture at the test section. But luckily for us, the domestic gas meters are operating at 1 bar pressure. So we were able to make some simplifying assumptions on the fluid properties side, but that wouldn't be possible at higher pressures.
Excellent. Is there anything else you'd like to add, Mark, today?
No, just that the projects I mentioned before, we're working on them right now, and every single one of them, the results will be open access. So it's either going to be a public report or journal papers which are open access, so you don't have to pay to see the results. So if you follow the GasMet project, for example, then all the project results will be on that website.
Brilliant. Well, all I can say is, again, thank you everybody for joining us today. As I mentioned earlier on, we will be sending you a copy of the presentation and recording. And also, as always, please feel free to visit our website. And basically, on behalf of myself and the presenters, I'd like to thank you for taking the time to join us today. And like I said, we will answer all questions that have been posted in. Thanks again. Enjoy the rest of your day.